Hey everyone, and welcome back. You know all those awesome calculus tools you've learned? Derivatives, integrals, all that good stuff? Well, what if I told you that you can use those exact same tools to describe motion through three-dimensional space? Today, we're diving into the calculus of vector functions, and you're about to see that it's way more familiar than you might think. So, let's start with the big question. How does calculus actually describe motion through space? I mean, think about it. The path of a satellite, the arc of a baseball pitch. How do we capture that with precision of mathematics? Well, that is exactly what we are going to unpack today. And here's our game plan. We'll kick things off with one core idea you have to know for calculus in 3D. Then we're going to find velocity vectors using derivatives and even build a tangent line. After that, we'll flip it and reverse the process with integration. And to wrap it all up, we'll talk about what this all really means. Ready? Okay, let's get right into it. Section 1, Calculus in 3D. Seriously, pay close attention to this next part, because this is the key that unlocks everything else we're going to do. This slide right here, this is the big secret, the whole shebang. If you are gearing up for some brand new, scary kind of math, you can relax. The secret to vector calculus is that you just do regular old single variable calculus 3 times. You just apply the rules you already know to the x component, then the y component, then the z component, completely separately. That's it. So let's see this big secret in action. Moving on to section 2, we're going to talk about finding the velocity vector. This is our first major operation, taking the derivative of a vector function. So just like we said, the derivative of a vector function, which we write as r prime of t, is just a new vector where each component is the derivative of the original. You take the derivative of the x part, the derivative of the y part, and the derivative of the z part. And here's the cool part. This new vector isn't just a random calculation. It has a real-world meaning. It's the velocity of the object at that exact moment in time. Okay, let's make this real. Imagine we have a position vector, r of t, given by t cubed, e to the 2t, and the natural log of t. We just go piece by piece. For the x component, the derivative of t cubed is 3t squared. Easy. For the y component, the derivative of e to the 2t, well, we got to use the chain rule, which gives us 2 times e to the 2t. And for the z component, the derivative of natural log of t is just 1 over t. Slap them all back together in a vector, and there you have it. That's our derivative. All right, so we can find this derivative vector. But so what? What's it actually good for? Well, let's look at a super practical application in section 3, building a tangent line. You will definitely see this again. Now, think back. To define a line in 3D, you need 2 things, right? You need a point on the line, and you need a vector for its direction. Let's find the point first. Say we're given a curve, this one's a helix, and a specific time, t equals pi over 2. To find our point, we just plug that time into the original position function. So we plug in pi over 2, do the math, and out pops our point, p, at 0, 2, pi over 2. Step 1, done. Now for that direction vector. This is where our derivative becomes the star of the show. The derivative vector, r prime of t, is the tangent vector. It literally points in the direction the object is moving. So first, we find the general derivative of our helix function. Then we plug our special time, t equals pi over 2, into that derivative. And what we get is our direction vector, v, which is -2, 0, 1. That's the exact direction of the curve at that specific point. And now we just put it all together. We use the classic parametric equations for a line. For each coordinate, it's just the point's coordinate plus the vector's component times t. So we plug in our point p and our vector v, and boom, we get the 3 equations for our tangent line. It's a perfect example of how the derivative gives us the instantaneous direction of a curve in space. All right, we have totally mastered derivatives, so it's time to shift gears. In section 4, we're going to look at integration, which is really just all about reversing that process. Now, you probably saw this coming. The rule for integrating a vector function is exactly what you'd expect. Just integrate each component on its own. But there is one little detail to watch out for. You remember the good old plus c from first-year calculus? Well, when you're working with vectors, that constant of integration isn't just a number. It's a constant vector, which we write with a capital C. Let's see this in action with a definite integral. We want to integrate the vector 4t cubed, 6t, 1 from t equals 0 to 1. And again, we just do it one piece at a time. The integral of the x component from 0 to 1 works out to be 1, the y component gives us 3, and the z component gives us 1. We just put those results back into a vector, and our final answer is 1, 3, 1. Simple as that. So we've hammered out the mechanics of how to differentiate and integrate vectors. But let's take a step back. What does it all actually mean? In this last section, let's zoom out and really look at the big picture. Okay, let's tie this all together. That derivative vector, r prime of t, we now know is the velocity vector. It tells you both the direction you're going and how fast you're going. Now, if you only care about the how fast part, you just find the magnitude, the length of that vector, and that's the speed. And this leads to a really important idea. If that derivative vector is never zero, we call the curve smooth. All that means is that the path doesn't have any sharp corners or cusps, which is a pretty big deal in things like physics and engineering. So there you have it. By just applying the calculus rules you already know, one component at a time, you can now analyze motion in 3D with some incredible precision. So that leaves us with one final thought. Now that you have this amazing tool in your toolkit, what kind of physical phenomena could you model next? The orbit of a planet? The flight of a drone? The possibilities are, quite literally, out of this world.